Okay, let's get started. So we were kind of going through some of the famous large language models, starting with the original one from Google. We discussed how this one was motivated for text translation, and so it has a bit of a different architecture where it has an encoder. The encoder does not have causal masking because its goal is to take the input context and turn it into just sort of extract all the meaning, and then it passes that meaning as a latent vector to this decoder network. The decoder network does have masked causal attention because it does do autoregressive text generation, but it is generating text with the specific meaning that is coming from the original language. Okay, so this gives us the encoder architecture and the decoder architecture. Although when people refer to the decoder, they usually don't. They usually don't have this part here. Okay, so we'll focus a lot on OpenAI's models because it has often been kind of at the forefront of language models, and it has a pretty nice story to tell over its different generations. Although keep in mind, other companies have also had language models, similar ones at around the same time. So we said that the original GPT model was special because it proposed to pre-train on next token prediction, which is exactly what we've been focusing on for a lot of these notes. And then as a second stage, fine-tune for a desired task like acting as a chatbot. So we will talk about fine-tuning later, but so far we've only really talked about the pre-training part. So it uses a particular encoding scheme with 50,000 tokens, and it's a decoder-only model with 12 transformer blocks, 12 attention heads per block, embedding dimension of 768, context length of 512 tokens, and 117 million parameters. So it was trained on a corpus of unpublished fiction books, so about 1 billion words, taking about 1 petaflop second days and costing about $50,000 at the time. So we'll sort of track a lot of these numbers over time to see how things have changed. So I guess there's a number of these parameters we can look at. Okay, then we also briefly talked about BERT. So BERT was Google's model that came out just after GPT, and BERT has this word bidirectional because this is an encoder-only model. It doesn't use that causal masking. It was not pre-trained for next token prediction, but rather it was trained to predict a randomly masked word in a sentence and also whether one sentence followed another. So after you do that, you can then replace the final layer and fine-tune this for a specific task. So this used a pretty similar vocabulary size, a slightly different tokenization scheme, similar numbers, context length 512, embedding dimension 1024, 340 million parameters. So this is a bit bigger. It's maybe roughly twice or 3 times the size. But in terms of the training data, instead of using 1 billion words, this used 2.5 billion words. And this took 6 petaflop per second days and cost around 7K. So we noted that actually, even though it's 6 times as much computational effort, it's actually cheaper just because the hardware had evolved at that time. Okay, so that's BERT. And then we go to GPT-2. So this is February 2019. One thing to note about GPT-1 and 2 is that these models are open source and open weight. So what open source means is that they told you things like the architecture, this is how we trained it. They give you all that information, in some paper. And then open weight means they actually allow you to download the trained coefficients. Sometimes models are open weight but not open source, so they give you the pre-trained coefficients, but they don't tell you how they got them. And then sometimes they're open source, where they tell you how they train the model, but they don't let you download the weights. Okay, so it's pretty similar in architecture to the first GPT, but one notable change is that layer norm was moved from coming after the attention and feed-forward network layers to before, because they figured out that this made the training more stable. So this is known as pre-layer norm, and after they did this, this became sort of the standard used by everyone else. So the vocabulary size is, I think it's quite similar to GPT-1, 50,000 K, byte pair encoding, but the number of coefficients you can see grew from 100 million to 1.5 billion. Context length is pretty similar still. But now instead of 1 or 2 billion words, it's 10 billion words. And this is 28 petaflop per second days instead of 1 and 6 that we saw earlier. And this costs about 50,000. But it's interesting, there was a blog or something that said if you tried to do this in July 2024, which was basically like 5 years later, instead of 50,000, you could have done this for less than $1,000. Because again, the hardware had evolved. Okay, so that's GPT-2. Oh, I forgot to mention that one special thing about BERT is that this was the first model to show human-like performance. So, performance that people were really impressed by that wasn't obviously fake. Okay, so GPT-2 was a little bit of an advancement. Then GPT-3, let's see, this is maybe about a year later. It's once again, they didn't really change the architecture much, but they just made everything bigger. So this one had more transformer blocks, more attention heads per block. The embedding dimension grew from 1,600 here to now 12,000. Context length doubled, but the size of the model went from 1.5 billion to 175 billion parameters. And then the training data went from 10 billion, let's see, it says 10 billion words. I'm not sure how many tokens that was, but now 800 billion tokens. So training data is going up considerably. And in terms of the computational effort, instead of 28, this is now 3,600 petaflop second days. And at the time, they did this using a Microsoft-built supercomputer with 10,000 NVIDIA V100s. These were the top-of-the-line GPUs at the time. And it took 34 days on this supercomputer. This would have taken 355 years if you only had a single one of these. And at the time, this is now costing millions of dollars. So this was a huge step up in effort. And an evolution of this model, which was GPT 3.5, was the model used for the first version of ChatGPT, which came out in November 2022. And if you remember, that was like a huge thing, like even in the popular press, popular media, basically, this was in some sense like the start of the chatbot revolution. 100 million users in 2 months. And then we'll talk about this later, but this was fine-tuned using reinforcement learning with human feedback. We'll talk about what that means later. And there's a nice, I think it was a nice set of videos I found which showed exactly where all those 175 billion coefficients come from. If you can make a list of all the different weights. So we have the embedding, and this is going to be, it has a particular embedding size, particular vocab size, which we know are these numbers. So this is going to be a matrix with 617 million coefficients, and then you have your positional embedding, which is another matrix of size, embedding dimension by context. So this is another 25 million parameters, and then you have the key matrices. They are all going to be 12K by 12K, but now there's one for every layer in the network, and there's 96 layers. So here we have 14 billion 14 billion coefficients, similar for the queries, keys, or the queries, the values, and the output. And then you can see that actually the biggest part of these models are the linear coefficients in the feed-forward network, the MLPs. So these each consume 58 billion parameters. Remember, that's where they store the facts, so it's thought. There are bias terms, but they really don't amount to much. And then you have layer norm has its own learnable scaling and shift, but that doesn't amount to too much. So that's how you get the 175 billion parameters. Right. Any questions so far? Okay. All right, so then the following year, GPT-4 was introduced. So the innovations in this model is that it is multimodal. So this model natively handled both images and text. Also, they figured out that it was more efficient. Rather than just making a single model bigger, they split it into 16 different models that are called experts. And each of those experts had an architecture similar to GPT-3, but with more parameters. And then there's some kind of logic or learnable mechanism to kind of like poll certain experts at inference time. So you don't have to talk to all the experts. So this cuts down on the inference cost, but also it was a better way to scale the model. They couldn't have gotten the same performance with a model that's 16 times as big. It was better to split it up into individual models that were experts on different things. Okay, so a lot of the details are not known. They're proprietary, but people think that there were 16 of these experts, and so this network is a little deeper in 796. It has 120. The context length, what was the context length here? Was 2048, so now that's 4 times as big. I guess I don't know. So, okay, yeah. Well, let's see. Okay, so we have, I don't know exactly why. So this says it's more parameters, but actually instead of 175 billion, it's only 111 billion per expert, but then in total you have 1.8 trillion parameters for the total model. Nobody knows what the data was, but they think they used 13 trillion tokens. And so if you look at the computational effort, GPT-3 was 3.6 thousand petaflop second days. Now this one is 230,000 petaflop second days. So now the state-of-the-art NVIDIA GPU went from a V100 to an A100, and they had a server with 25,000 of these that allowed them to train this network in 100 days, costing them about $70 million. And there were various evolutions of this within the GPT-4 family. One that was very kind of famous because it was used for a long time, although I read today that it's getting discontinued, is GPT-4o. This is basically kind of a lightweight but good performance model. This one is multilingual and multimodal, but it also handles audio, not just text and images. And the context length, so with the context length here you see is 2048. Here it's 8,000, but now context length is 128,000. So that is being scaled. This one costs $10 million to train, and then GPT 4.5 was introduced about a year ago, and it's one of the last non-reasoning models. We'll talk about reasoning models in a moment, and I think it's probably the biggest model they ever trained. It costs them about $400 million to train it, and it's also very expensive for inference, so I don't think they allow anyone to use it anymore. But one notable thing about it is it passed the Turing test. How many of you guys know what the Turing test is? The Turing test was proposed by this guy Turing just after World War II, that he said, if you set up a situation where you have a typed conversation with someone on the other side of a wall, and a machine makes you believe that you're conversing with a person, then that is going to be kind of a big step in artificial intelligence. And so this passed that Turing test. So this, yeah, okay. All right, any questions? Yes.
Under mixture of experts,
yeah.
how do those, do each of the experts get your entire prompt, and then is it stacking, or how is it decided which expert responds?
I'm not exactly sure. Maybe if you click on the green link, it explains it more. But I think that they want to prevent all the experts from running all the time to save costs. So I don't think the experts will be, they probably won't all get your full prompt and run. I think there's going to be something that screens your prompt and then passes it to maybe one or two experts.
Gotcha.
And then you'll, and then I'm not sure how the outputs are synthesized from there.
Gotcha.
Okay, any other questions? Okay. All right. So so then in the kind of 2024 time period, the frontier models, they shifted away from the ability to immediately generate a response to what's called chain of thought reasoning, where they think through problems methodically, show their work, self-correct along the way. And this is especially important for complex reasoning tasks like if you're doing coding or math or science, and you cannot have them just make stuff up that's not true. The disadvantage of this kind of style of operation is it takes longer to generate the output. It's not as instantaneous. So if you're doing something like conversing with a chat bot who is, over the phone, you notice if there's a delay in the conversation. It sounds fake, it sounds wrong. And so you want a very quick output. And what was impressive about some of these models here is that they could natively handle audio. So it's because previous to this, if you were talking on the phone with the chatbot would generate text, and another model would take text and generate speech. but that process was pretty slow. And so it was pretty obvious that this is a weird conversation. Like, this person is always taking a few seconds to respond. But once they had audio native, they could immediately generate the response, over the phone, and it would sound very real. Okay, so these reasoning models, they're not as fast that way, but they have the ability to do more complex things and hallucinate less. So the first one from OpenAI was their O1 model. This is September 2024. And while earlier models, you could get them to reason by prompting them to reason, this was actually trained specifically for reasoning. So reasoning was part of the pre-training, I believe. I'm actually not sure if it was in the pre-training or post-training, maybe just in the post-training. And then O3 was an improvement a couple months later that used multiple reasoning paths for better performance. O4 Mini was maybe 5 months later. So this is fast and cost efficient, and the context window now is 200K. Also, this can deal with visual inputs like diagrams, handwritten formulas, sketches, things like that, which is very useful, as you know. And then most recently, we have GPT-5 released last fall. And so the maybe notable thing here is it merged reasoning and multimodality, and it has a 400K context window.
How does that reasoning work? Like, is the model just...
We'll talk about that.
Oh,
Yeah, we'll talk about next. Yeah. Any other questions? Okay. All right. So we won't talk about it on this slide, but we'll talk about it in a few slides. Okay, so then at a high level, what happened next after reasoning models was the return of open source models. And so, as I mentioned before, the early large language models like GPT-1 and 2 and BERT, they were open source and open weight. But then starting in 2020, these companies became very secretive. They didn't want to let other people know what they were doing, and so the designs were very proprietary. But then Meta's first version of Llama kind of led a return to open source models in February 23. Also, there you see a few new tricks. So one of them is, instead of using the GELU activation function, they use this swish or swiglu activation function. They used, instead of regular positional embedding, they used something called rotary positional embeddings. And instead of layer norm, they use RMS norm. And I don't know if they did that here, but another thing you see now is you see RMS norm placed before and after both the attention head and the feed-forward network. So there's like 4 RMS norm stages per transformer block. And there were a number of Llama versions. The most recent is version 4, released about a year ago. This one is mixture of experts, multimodal reasoning. And then another thing that was a big splash was in January 2025, Chinese company DeepSeek released their R1 model, and this was an open source and open weight model, reasoning model. What was special about it is that performance was on par with OpenAI's O1, so it wasn't like state-of-the-art that way, but it was trained with a very small fraction of the training costs. So the idea was that if you have to spend hundreds of millions of dollars to train models, then that says that only these few companies are going to be able to do that. But DeepSeek showed that no, actually a much smaller company with much fewer resources is able to train a very strong model using a combination of, they did to some extent use existing models through some process called distillation, but they also had a lot of clever advancements in the idea of actually the training process. One of the things that was interesting is they showed that chain of thought reasoning could emerge purely through reinforcement learning without any human intervention. And we'll talk about these things in just a moment, but that was kind of another thing that this model is known for. And nowadays, there's almost everybody has their own version of an open source model. You have several Asian models beyond DeepSeek. You have like Alibaba's Qwen and Moonshot's Kimi. There's some French models by Mistra. Google has Gemma, which is different from Gemini, which is their closed source model. The older Groks are open source, but not the current ones. OpenAI has their own open source model, although I don't think it's that competitive with the other ones. But anyway, so now you have all these open source models, which is cool because you can actually see what people are doing, exactly how they're architecting and training their networks, which is very interesting. But then it also means that if you have the resources, you can potentially run these things locally and modify them and do things like that. Okay, any questions? Okay. And then the current thing that's happening is AI is maturing from large language models that simply respond to prompts to AI agents, and these are entities that autonomously plan, execute, and adapt to accomplish complex goals. Like if you want to say, book me flights to the Super Bowl, it's able to figure out what you mean. It has to know about your preferences. It has to know about your information, your frequent flyer number, your credit card number. It has to be able to go to it has to be able to search for the cheapest flight and then go and book it, and all that stuff. And so they basically reason through multi-step plans. They invoke external tools and APIs. They have to maintain memory across your many interactions with them. They have to verify their own results, recover from their own errors, all with minimal human oversight. And so some of the notable ones these days, OpenAI's Operator, Anthropic's Claude Computer, Perplexity's Computer, and recently making a huge splash is the open source method, OpenClaw. Okay. So that's just kind of like big picture how things have evolved. And now we'll come back to this post-training that we haven't really talked about much. Okay, so what we did talk about was pre-training. And as we discussed, pre-training nowadays is you're training a model for next token prediction on a massive text corpus. But if that's what you have, then the behaviors that you see are things like memorization. So if you trained on Wikipedia and now you give the first sentence of a known Wikipedia article, the model will perfectly regurgitate the rest of the article. It has basically memorized all this stuff. But if you give it the first sentence of an unknown Wikipedia article, which it has never seen as pre-training, then it will confidently make up a fake article, and differently every time you run it because there's a lot of randomness to that autoregressive text generation. So that is known as hallucination, when it's basically confidently giving wrong information. Now, sometimes you want a model to hallucinate. If you say, like, write me a poem, you're explicitly asking for hallucination. Or if you say, like, draw me a picture of this. But hallucination is usually means, like, you want a fact, it gives you the wrong fact, and it does it in a way that's very confident that prevents you from realizing that it's a wrong answer. Okay. And then another kind of amazing behavior in these pre-trained models is known as in-context learning, which is basically they can do tons of stuff that you didn't train them explicitly to do. There's many examples of this, but here's one example. Is if you give it a sequence of English-Korean word pairs, and then finally an English word, it will translate, and it will give you the Korean translation of that word, even though you never explicitly trained it to do that translation. It just kind of has learned with all of its training data, all those associations. And it can do all kinds of interesting math too, even though you never trained it to do math. There's lots of examples of in-context learning. But what's missing is that this is, for example, not yet a chatbot. It's not yet a coding agent. All it knows how to do is just next token prediction. It hasn't undergone what is known as fine-tuning. Fine-tuning is the process of adapting this next token predictor to a given task, like a chatbot or coding agent or something, and also aligning its behavior, meaning making sure that it is not like, giving information that is racist or dangerous or unhealthy or things like this. Okay, so supervised fine-tuning is usually the first stage of the pre-training. And here you're adapting it to a specific task. So for example, maybe you want this thing to be a chatbot or a translator or a coding assistant. And so what you do in this stage is you carefully construct a data set of conversations that show how you want it to behave. So for example, also you can include new special tokens for this purpose. So for example, common tokens would be like system user assistant, which basically tells, or the system learns, the LLM learns that these things have a meaning, and that the meaning of the system token is, the next sentence here is going to be kind of a high-level system instruction, and then the user says, okay, now the next thing is the user instruction, and assistant, this is how you should respond. And so the goal here is to make the assistant helpful, truthful, and harmless. Initial stages use human written conversations, but then, we can't generate enough of those as humans, so later stages will use synthetic conversations. So the LLM will generate conversations and then train itself on those. And we'll talk about more details in a bit. Okay, so this is SFT. Any questions on this? Okay, so let's just also reflect on a few things that sometimes there's a misunderstanding. So if you ask an LLM a question like, which model are you? It really, what it tells you will reflect how it was fine-tuned. It's not going to tell you some like true information. It's going to treat this as kind of a next token prediction task. So if you're just working with, a model that has not been fine-tuned, to do anything particular, it's probably going to respond with the most common model that it has seen in its pre-training, whether that's what it is or not. So maybe GPT-3 is, very famous model, so maybe it just responds, I'm using GPT-3 even though it's not. But in the fine-tuning, you could have explicitly instructed the chatbot never to reveal its model, if that's what you want. Or you could have taught it, you are this model. So it's really just a matter of what you trained it to say. Okay. Another thing about, as we saw with the issues with the pre-trained only models are hallucinations. So there's different ways to mitigate unwanted hallucinations. One is to train the model to admit when it doesn't know the answer. So one way you could do that is you probe the model on many questions for which you know the true answer, and then find the subset of questions where the model answered incorrectly, and then come up with a new conversation data set, where the answer to those questions is I don't know. So you figure out what it doesn't know, and then you train it to say, I don't know, when it doesn't know. Okay, so that's one way, admit when it doesn't know. Another way to mitigate hallucinations is to train it to use tools. Like if you try to do arithmetic with a pre-trained only model, it probably is going to confidently give you totally made up answer, because unless it has seen that particular math problem in the text, like if you ask it 1 + 1, it's probably seen that a lot. It knows what that is. But if you come up with two large numbers that you ask it to multiply or add or something, it hasn't seen that before, it's just going to make up an answer. So if you want it to not do that, you can have it learn to use tools. Like you can have it say, oh, I'm going to go call my calculator function now, and then I'm going to return that to the user. Or you can have it, if you ask it about a current event and that's not in its pre-training, it can go and it can search that on the web and then return that answer for you. So that's another way you can do that. And for this, you might introduce new special tokens like search start, search end. And if you play with modern large language models, you can prompt them to use tools or to not use tools, and you will see that has an effect on the answers you get. And then third thing you can do is you can train a model to carefully reason about logical problems, and that's the chain of thought reasoning, which we will discuss next. Any questions? Okay. So before we get into the details, let's reflect on a few interesting things. So the goal here is, can we get these models to do logical problem solving? So an important fact is that the amount of computation per token is basically limited. So, the model has a total amount of computability and memory and all that stuff, right? And it has a context window, and then if you can basically say, like, then per token, this is as much thinking as I get. And so that's going to be limited. So if you really try to do a massive amount of thinking in one token, there's no way to do that. So to get around that is you should distribute complex question and answers over many tokens. That is how to get around this issue. Spread your information over tokens. When spreading your information over tokens, you want to make sure there's no big jumps in logic, or you want to make sure that it's very gradual, very incremental steps of logic and ideas. So causal and gradual. And so when you see a model give you an answer where it broke everything down into many different steps, it's not doing this for you. It's actually doing this because this is how it works best. Right. It's making its job easier by spreading things out. And you can also change this behavior through prompting. You can tell it to distribute over many tokens or explain yourself, and that will generally improve the quality of the responses you get. Or if you say, answer instantaneously, you can actually make it shortcut those and give you more hallucinatory, worse answers. Okay. So another thing to reflect on is that these models, in many ways, are extremely smart and impressive. They can do all this complicated physics and math and stuff, but then there's a lot of very simple problems where they completely fail. So a few examples of these would be if you ask it to print every third character in the word ubiquitous, it's going to have a hard time doing that. And the reason why is because, we see all the characters in the word, but it doesn't see those characters. It just knows this as, a couple tokens. And so you're asking it to do something which is really kind of against its nature. It's kind of like asking a human to, compute the cosine distance between two words. It's that's not how we think. But the model could do that very easily. Okay, if you ask it, how many dots are here? Again, it hasn't really been exposed to that kind of problem in its training, so it's just going to struggle, even though a human would find that very easy. And other things, like if you asked which of these is number 9.9 or 9.11, you may get confused because in a lot of text data, when you have different sections, like in the Bible, section 9.9 might come first, and then section 9.10, 9.11. But if you think about these numbers as decimals, then it doesn't work that way. So if they've been trained mainly on text data, they might not interpret those as mathematical kind of numbers. So important to think that these things just work. They think differently than us, so that means that we can't make assumptions that certain things should be easier for them or hard for them because they're just different. Okay, and then one other kind of tool that we have at our disposal is something called reinforcement learning. This has a long history. It's kind of a field of study on its own that existed for decades. And in reinforcement learning, the goal is to train an intelligent agent to take optimal actions in a dynamic environment. As a simple example, you want to build a chess playing computer. So you wanted to take actions, meaning move pieces on a board in a dynamic environment because as the opponent does the same thing, the board state changes quite a bit, and you have a goal. Your goal is to win the game. So roughly speaking, RL kind of works this way. You have this agent that is something making the actions. The action is a particular thing it can do depending on the situation. So if we're talking about chess, it can move any of its pieces through one of their allowable transitions. That affects the environment, which in the case of chess would be the state of the board. And then given the current environment, sometimes with a chessboard, the state is finite. It's very easy to describe it, but there's many other situations where the state is not fully known. Like something happened and you have a partial observability on what has actually changed. So because you don't know exactly, you may have to interpret it. And you may have to estimate the state. It's not something that's obvious. And you may have a bad estimate. But in any case, whenever you make that action in the environment, you can say, oh, the environment changed. Is it better or worse? What happened? Did I improve the environment according to my goal? So that would be the reward. And this happens in a feedback loop, around and around and around. Different flavors of reinforcement learning have different knowledges about, whether this is known or unknown, how that's modeled. In some cases, this is a complete black box. In other cases, you know exactly how that works, like chess. So it really depends on the flavor of the problem. But in general, with reinforcement learning, the current environment is modeled as a state, which is going to be some discrete number or maybe some vector, maybe continuous vector. When the agent makes an action, the current state changes to a next state, and an immediate reward is collected. But your goal is not to maximize the immediate reward, but rather usually some long-term reward. Like in chess, you want to win the game. In order to win the game, maybe you have to sacrifice your pawn at the moment. So immediate reward is, negative, but long-term, this is going to help you. And one of the main ideas in reinforcement learning is the exploration-exploitation trade-off. So which is the trade-off between if you have some, let's say, current understanding of chess as a game and of your opponent, you could act in a greedy way to always make the moves which maximize that instantaneous reward, or even your prediction of a long-term reward. But because your understanding of the situation, the opponent, the game is limited, you may not be acting very efficiently. So maybe what you want to do is you want to do some exploratory moves to try to get a better sense of your opponent or of the game, with the goal of being able to have a better understanding to then play better in the future. So that's kind of the trade-off. Do I explore or do I exploit? And all models have to get a happy medium and have to make that decision at every step. Some balance between those two objectives. Okay, so that's kind of reinforcement learning at a high level. Any questions? By the way, there's a whole course on reinforcement learning taught by ECE. I think it's going to be offered in the fall again. Yeah, I think it's a fall course. And it's supposedly taught, it's a 7,000 level course. However, it is important for a lot of master's students for their master's projects. So it is not supposed to be taught at like a very theoretical level. It's supposed to be, and it doesn't even have machine learning as a prerequisite. So I think any grad student could take it. Or if you are a senior undergrad and you've maybe taken this course, you could probably ask the instructor if you really wanted to. Yes?
Why are these still called large language models when they probably should just be like large prediction model, or like, obviously we're not just training on language.
That's true, yeah. I don't know. Maybe they're just called models. Maybe, yeah. But you're right, they're multimodal now, so it's not just about language. So if it is being referred that way, it is just kind of a holdover.
Yeah.
Okay.
Here the reward could be negative, right?
Yeah, it could be, right. The instantaneous reward could be negative, and then, so there's different ways to formulate the long term. It could be only the final reward, or it could be average over time, or there's many flavors of how you set it up mathematically. Okay, so that's reinforcement learning. So finally, with all those things, let's come back to LLMs. So we learned that for tough problems, we want to spread out questions and answers over many tokens, but tokens are expensive, so we want to minimize how many we use. Also, we know that these models think differently than humans, so our ideas of teaching may not work for them. So how do we actually construct these efficient training conversations? And so let's first talk about the case where we are working on problems with known answers, like we're doing coding or math. For this, we can use something called reinforcement learning with verifiable rewards. So this is RLVR. Basically, the way this works is that the model itself generates many answers or many reasoning pathways, each of which can be verified as being correct or incorrect. And then you do an update of the weights of the model so that the correct answers are more likely. So here, what's different than just a human making up all these conversations manually is that so there are problems. Sometimes they can be synthetically generated problems, right? But the model is randomly generating all these answer strategies. And now you can train on which one of those are good or bad. Okay, so there's a sort of a feedback loop of reinforcement learning going on here. So if you step back now and you think about, at a high level, how are we educating these LLMs? So first stage is unsupervised pre-training, which is kind of like telling these models to just read a whole bunch of textbooks to gain very basic broad knowledge. Second is supervised fine-tuning, which is like reading worked examples of the sort of problems that you want them to work on or to be good at. But so far, this is just all passive, just reading. This last step, RLVR, is more like active learning. So you're asking it to solve practice problems, but you have this answer key. Okay, so basically, it's kind of at a high level what we have here. All right. Any questions? Yes.
Yeah, so the last step is not let it acquiring new knowledge. It's just letting perform more stable on the questions that it already know the answers?
So you're asking it to kind of, so there's sort of randomness. The model is kind of part of generating the conversations that it is being trained on.
Yeah.
But yes, you have to have these verifiable answers. So it's like, that's kind of the constraint here. Maybe you can generate these coding problems or math problems randomly, so you don't need humans to do it. So this is all automated. It's not limited by like how many humans you have working on it. And then there's this feedback loop. You're using reinforcement learning to kind of continually improve and learn about how should I generate answers, and so on and so on.
Right. Gotcha.
Okay. So what if we don't have verifiable rewards? For example, like you want to have it write a funny joke about something. Well, you know, you could have like a bunch of humans scoring like whether the jokes are funny or not. But the problem is that we just don't have enough human scorers to do that at the scale we need to train these models, or at the speed we need if they're being used in this reinforcement learning loop. So instead of having the humans as scores, you can instead train a model of the human scores. So for this, you start with humans ranking a handful of responses, maybe to a few thousand queries, and then you train a reward model to predict the human scores. And now you use that reward model instead of the humans in the reinforcement learning loop. And so this is called reinforcement learning with human feedback. So this is tricky stuff because the reward model is not perfect, and it is also easily gamed or tricked by the the language model. So often when people try this approach, they have to stop things early before things go out of control. So this is an evolving, all this stuff is evolving, and there's a lot of details here that I'm not going to get into and that I actually don't know all that much about because everything changes so quickly. But there's a lot of great blogs that get into these details if you're interested in learning more. Okay, and I have some resources in just a moment. So finally, quest for superhuman intelligence. So basically, you know, people talk about this, so what does this actually mean? Well, this is actually possible because humans think, you know, in particular ways, but these machines can learn new ways of problem solving that humans don't have or haven't figured out yet. And there's some concrete examples of this. So there's a very complex board game, Go, and you have people like spending their whole lives doing nothing but learning Go, and you have, you know, hundreds of years of human experience trying to master this game. But they trained a model AlphaGo, to play this complex game, and it beat the top ranked Go players using strategies that were previously unknown to humans. So it really came up with, you know, new ways of thinking about the game. Then that was the first round in like 2015 to 17 with AlphaGo. And this is all Google. Then they evolved these strategies with AlphaZero and MuZero just to the machines taught themselves to play a number of games like Go, chess, shogi, Atari games. So here, these were like self-taught. There was no humans like doing initial training of these models saying like, here's some great strategies from the Go masters. Now, you know, using these strategies, try to do better. It was like, no, just from absolutely nothing, these models figured it out. They then used these ideas with AlphaFold to predict 3D protein structures. This won the 2024 Nobel Prize in Chemistry. And another example is AlphaDev, which discovered new state-of-the-art sorting algorithms. And there's many other examples, but these are just a few concrete ones where you have these machines doing things better than any humans have done. But the limitation so far is that these are all specialized endeavors. The thing that people are, pushing towards is the artificial general intelligence, where you have methods that can kind of tackle anything. So that's the frontier. Let's hope it doesn't happen. Okay, so there's a lot of good references that I drew from for these notes that I can recommend if you want to learn more. I think I mentioned this before, this Andrej Karpathy, he's just an amazing educator and engineer. He has a great series of networks that go through how to build things in PyTorch. Zero to Hero series. Each video is about 2 hours long. There's a really nice blog that's already a few years old that I stole all the images from for Attention Transformers. I don't know if you guys know this 3 blue, 1 brown YouTube videos. They're great visual explanations of many cool engineering and math things. So they have some nice videos on LLMs, Transformers, Attention. I stole a picture from them. The post-training stuff I got mostly from this, again, Andrej Karpathy video that goes into, a lot of what I said, but in more detail, 3.5 hours. If you want to go beyond what I presented here to really see what is happening with evolving architectures and training methodologies, Sebastian Raschke has a really great blog with many articles about, he's very up to date. He's constantly writing about the latest models, how they look, how they're architected, how they're trained. If you have the time to spend on it, you can take a Hugging Face free course for 100 hours on LLMs and really how to program them. Hugging Face is really more than PyTorch. It is the place that has all these models and all these transformers. And if you want to keep up with the latest leaderboards and stuff for the latest models, there's various places to do that. So that's enough for today. We'll just have maybe a part of a lecture. We'll learn about Scikit LLM, which is a cool little package that allows you to interact with all these state-of-the-art models and use them to do things maybe that you want to do very easily in a kind of scikit-learn type framework. So we'll talk about that next time, and then we'll move on. All right, have a great weekend.